right, good morning everyone. So there was not supposed to be a stream today because I had plans, but my plans got cancelled, and I kind of was in the mood for writing some graphics code. And then the problem is I'm trying to write the graphics code for this project on stream to the extent possible. So I thought, should I just not write this for a week? Should I write it off stream and then, like just show people diffs at some point in time? And then I thought, well, there's no rule that says that I can't just randomly start a stream. And so I just randomly started the stream. And so we will write some graphics code today for some things that I wanted to do since the last Niagara stream 2 weeks ago. Since then, nothing much has changed in the code as far as, important things go. Well, that's a lie. Hold on. I started playing with some material stuff and I stopped before it was too late in an attempt to write more code on stream. So I did that specular after the last stream. Let me kill this. So the renderer looks almost exactly like we've left it 2 weeks ago. I just hacked in some specular highlights. This should be how it used to look. I did do a little bit of infrastructure work. Most significantly, I implemented shader reloading, which I will not talk about. You can, like, the implementation is very unsophisticated. Just I can press a button and then every frame it will just load shaders from disk. And then I can change GLSL code and then have the shaders like update. This is the code for this is very simple. You can look at this in the GitHub repository, but this will I wanted to do this in preparation for the material work. So yeah, I'm just gonna write some code and then we'll see what happens. So the goal is to make the scene look nicer. The first thing, hold on, let me, unfortunately I don't, actually, yeah, I guess the way we will, shader reloading helps when you can just iterate on shader code, but I will need to iterate on the C++ code a little bit. So first, the goal is to expand material rendering. For this, I need to have more material data. The first problem that I hit when I was playing with this off stream is we actually just dumped a bunch of extra data that is material specific into our mesh structure. And I didn't notice this at the time because I wasn't carefully tracking performance, but this actually reduces performance of our kitten scene. Our kitten scene looks pretty bad now because it's like there's no shading on it. Why is there no shading on it? Oh, right, it's not that there's no shading on it, it's that shadow-like casting support is always on, which is another thing that we'll have to rework today for other reasons. But if you... Is there a way to make... Oh, I can make this always on top. Okay, perfect. So if I disable shadows, then nothing works. Wait. Oh. Never mind. Yeah. Okay. So like if I disable shadows, you can see kittens, but the problem is that when shadows is enabled, every single kitten is in shadow. I think I talked about this on stream before. There's like a cloud of kittens that cast shadows, and so it's impossible to see anything. Oh, and the other thing I added is basic camera controls. Again, I don't want to go into this on stream because it's like very, very, very basic code. People can look at this on GitHub. So the and then again, like actually specular highlights are not supposed to be here. This is how it used to look last time. So the first problem actually is if you look at the culling time, it's now 0.4 milliseconds. It actually should be 0.2 milliseconds, give or take. And the reason why this happened is because we added a bunch of data into our draw call structure, which doesn't seem like much, but actually this is 16 bytes, this is 16 bytes, this is 16 bytes, and this is 16 bytes. So this is plus 30%, like we made the draw code structure 30% bigger, which made things slower. And I'm about to add a whole lot more data that is material specific to the draw code structure. So the first thing I want to do is I want to move this to a separate buffer so that we don't suffer the consequences of kind of expanding the material data for this for this work. So and this is very, very trivial. We already have like a buffer which is too big for meshes, and then let's just add a buffer for materials. In addition, so we previously had like an array of meshes and an array of draw calls, but material data was embedded in the draw call structure. So instead of doing that, we will add a vector of materials. And then with images, we kind of do this thing where index 0 points to an image that's not like valid. It would be useful to keep the material index 0 as like a dummy index as well. GLTF data can come without materials, so when you load the scene from GLTF file, you should be prepared for having a feature of rendering geometry without materials. So of course, we don't actually have the material struct, but for now, my goal is to just pull this data out into a separate struct. And I should say I'm gonna go a little bit faster today than I usually do, because I will spend a little bit more time explaining, because I just want to get a bunch of things done, but the code that we're writing so far is not earth-shattering. So instead of having this in the draw call, we'll have materials. We need the same change on the GLSL side. So here, this stuff goes here. These can be uints, I guess. They were ints because I thought, we will use -1 as the no texture index, but we currently use 0 as the no texture index. And this shrinks mesh draw back to like 48 bytes, which hopefully will fix our current performance problems. Okay, so this is actually enough to, well, this will break GLTF materials, but I think this is enough to run our code to test the performance stuff. So let's just disable this thing so that things compile. And then, of course, in the shader, instead of reading the texture IDs from the draw call structure, we need to read them from the materials buffer. I actually wonder if there is some way to pull out chat so that I can glance at it occasionally. Wait. So yeah, so I need like a buffer with material data somewhere. I'm just gonna put it after the texture sampler. Some of this work. So the other thing that might happen is Intel announced the new like GPU, the Battle Mage or whatever it's called. I want to buy it and test ray tracing and mesh shading performance. I don't know if it's going to be available, because apparently people are already scalping it on Amazon for like twice the price. But if it is, then I want to test task shader performance there. So the task shaders are like slow and AMD. You should not use them. If they're also slow on Intel, slower than not using them, then I'd rather just remove them from the code. But maybe they're faster on Intel than not using them, and in which case I want to keep both passed. But anyway, so like the binding stuff is a little rough right now, which we will clean up later. So anyway, we added the material vector. We'll have to fill it later. For now, there's just one material there that's like a dummy material. And we have to upload this to the GPU. So we created a buffer. We should remember to destroy the buffer. wherever it is. And then we already have a bunch of code that uploads all of these buffers. So we will upload the material buffer as well. And then we have to bind them. Yeah, here. So we have like 3 possible render paths right now. This is why I want to remove task shaders, because it will cut the number of render paths from 3 to 2. But for now, we will just roll with this. So add it here, add it here. So in theory, this should be enough to run the code for the non-GLTF scene. And then on GLTF scene, the materials are going to be totally broken. Okay, cool. So I said the render time was 0.4 when I was just running this code, and now it's 0.3 again. So this is good, because this fixes, I think the render time was also 1.5 and now it's 1.13. So on this doesn't matter for Bistro, this doesn't matter when you have few instances, but I want to maintain the property of the code, which is that using a lot of instances is fast. Let me re-enable ray tracing. So now if I do run it again on Bistro, which should be safe, I should see a scene without any materials because we just broke materials for GLTF path. But it should be very straightforward, yeah. Because we moved the materials into a separate buffer, but we aren't actually populating this buffer with materials from GLTF. But this should be very, very easy to fix. So the way we will do this is whenever you load the scene, we will add more materials. We'll assume there is always a material, as I was saying, so that we can use 0 as a dummy index. Oh, and we actually should all right, so we should pass that in. So we'll assume there is always a material 0, which means that we can compute material index. Yeah, that is correct. So GLTF already has indexing for all of the references, including materials, so we'll just reuse that as is to keep things very simple. And then we will just copy this code. I'm not sure, I forget if we actually are using C++11. I guess we are. Oh, in place back without arguments is like C++ something else. Okay, so this is, I should have done this way to begin with when I was implementing GLTF materials. I was just being lazy and I just added the texture indices to the Recoding structure without thinking about what it would do. And what it does do is, in case you have a ton of instances, it inflates your Recoding size, and the Recoding structure is used like everywhere, and so that's not good for performance. Okay, so this is sort of preparation for for what's about to happen. Okay. So then what I want to do is I want to actually start using the material data from the GLTF file. And now I'm hoping, let's actually check that. So what do I need to fill? What are we missing? So it turns out that the Bistro scene doesn't actually look, if I launch it. Come on. Oh, I should build in the release now because I won't need validation anymore. This looks fine, but actually the Bistro scene looks very, very differently because we are ignoring a whole bunch of material attributes, which we should not do. So let me rebuild in release so that things load faster. And so what I want to check is if I just add like a bunch of data to the material structure. Now, in theory, this should not have any performance consequences for the case where there's a ton of instances. And if that is true, then we will be able to just populate the data from the GLTF file and have things work wonderfully, hopefully. Yeah, so this is still 0.3. This is 1.13, so I think this is all correct. Yeah, okay. So the hypothesis works. So now we need to extract a whole bunch of data from GLTF file. And then the other thing that we cut a ton of corners last time is the gbuffer setup. The encoding for a bunch of things was like not finished. I have a bunch of to-dos here. For example, we have three channel normal right now, and I was planning to use 2-channel normal with 1 channel reserved for like lossless and stuff. So we'll have to do this now. I have not looked into slang yet, and yeah, the pointer situation in GLSL is weird. The way buffer device is integrated in GLSL is like a little insane. I was actually looking into slang briefly, and then I tried to build some GLSL source that I have with slang, and slang compiler was very slow, which is an open bug on GLSlang repository. I'm not sure if they fixed it yet, but like the GLSlang compiler, or the slang, sorry, compiler takes like 2 seconds per shader run in the default configuration due to how it's bundled. So I just, ignored it. But yeah, it might be worth switching to slang in the future because clearly GLSL is showing its age in some of these modern GPU programming constructs. So we don't have fragment shaders. We don't have an ability to switch fragment shaders. This is sort of correct, except that we can run more passes with different I think we're already doing this. So to some extent, we can run more passes with. Okay, there's 2 problems. One is we are using bindless, or not bindless, like draw indirect. We have like O of 1 draw calls. And so we have a very constant number of pipelines that we use right now. This problem is solvable. You can just have more than, as long as you have like 4 BRDFs or whatever, you can, in theory, just render like 4 kind of buckets of draw calls. The bigger problem that we have is we have switched to deferred shading. And so once we switch to deferred shading, there's this problem of how do you shade with more than 1 different shading functions. There's a way to solve this, which we might get to this eventually, I'm not sure. I was planning to reserve, you normally don't need an infinite number of BRDFs. There's a recent Baldur's Gate talk from Graphics Programming Conference, and I think they talk a little bit about their shading setup. And I think they have 8 or so material types, BRDF types. You probably can get away with fewer than 8. So I was planning to just encode the BRDF index in the future in the gbuffer and then just do some sort of tile dispatch, we'll see. The bigger problem is transparent objects. I haven't decided what I want to do with transparent objects yet. So we'll see one step at a time. I think for now, essentially the goal is can we get better looking materials and nicer looking shadows? And I will try to spend less time on materials and more time on shadows, because shadows are more complicated. So I just want to plug in a bunch of data for materials for now for things to look better, and then we will see where this leads us. Anyway, where this takes us. Okay, so let's go back to the material data. What data are we missing? So the problem is when we extract all of these textures, GLTF file has a bunch of multipliers for the data in all of these textures. So for albedo, for example, it has, we have like 2 different extensions, but it has base color factor or diffuse factor. And then metallic factor, roughness factor, specular factor, glossiness factor. There is this problem, which is there's 2 ways to specify materials in GLTF. and this is the modern way, but unfortunately bistrocene uses the older way, sort of the older way. This extension is deprecated now in GLTF, and this kind of means we have to do things for this extension for now, and then in the future try to convert the scene maybe and just switch fully to metallic roughness. I don't want to go too far into the specular glossiness route, just because it's too much data in gbuffer and stuff anyway, and many people are not using this. Many people are using metallic roughness. Anyway, so the point is we are missing a bunch of factors. So we need diffuse factor, which is also going to be in the alpha channel. You can have like the extra translucency multiplier or whatever. So then for the specular, let's just call it specular factor, and this is, we are missing specular color and glossiness multipliers. And then the other thing we are missing is the emissive factor. And the emissive factor turns out the lights in Bistro are actually different colors, and it's just the emissive factor is used to control that. So these are the three big things that we are missing. And then once I fill them from the C++ side, I think we'll be able to just use shader reloading to like to work with the data without like rerunning the application and stuff. So, and so here again we have to like, oh, actually should I, while we're here, let's rework things a little bit. Okay, so first of all, diffuse factor should start with 1, and then the other factors can be 0. I think they should be 0 by default. And for the dummy material, we should also make sure we can use some like weird color for this material, but I think for now we'll just keep it as white. So if there is a metallic roughness extension, then everything is like everything is 0 by default. So I think we can simplify our code a little bit by just checking which extensions are present. PBR specular glossiness. So this stuff goes here and here. We'll use an if statement. Okay. So, oh, but we still have to, okay. I'm not sure that this is a lot of simplification of the code. So the problem is basically we just need to extract the factors from different places depending on which extension is used. This if is really obnoxious. Wait. Was there even correct? Oh, I didn't handle the roughness stuff at all. I guess that makes sense. We'll ignore the roughness portion for now because we can't even test this. But if you do use the metallic roughness extension, then this base color factor field in GLTF is where the diffuse multipliers come from. And then if we use the specular glossiness extension, which is our main thing right now, because this is what bistrocene uses, then so we have the diffuse texture, and then we have the specular texture. Oh, wait. Okay, and then so then here we should apply diffuse factor. That's correct. And then we should apply a specular factor. That is correct. Okay. Copilot suggestions are very on point today. I think that's... Oh, I forgot emissive factor, sorry. All right. So I think this is it for the data that we need from the scene. Let's see if any of this works. So I enabled shader reloading. I will keep this always on top. One thing we can do, for example, now is we can say, well, instead of albedo, let's get the emissive color from the material, the emissive factor from the material. Okay. So yeah, so as I was saying, like, as you can see, these lamps are actually colored. And we didn't know this before because we were ignoring GLTF properties, right? And now we aren't. So now what we are going to do is we're going to apply all of these individual factors to the material properties, and then we're going to figure out some specular stuff. So I talked about deferred shading last time. We might go for a visibility buffer in the future. Deferred shading was the quickest way to go from a forward setup to a deferred setup. Forward setup doesn't work for us because of ray tracing. The cost is too high. The first problem is just using ray tracing, and the fragment shader has an extreme cost because of various types of overdraw, and depth prepass solves some of them but doesn't solve them fully. The second problem is I want to start doing a lot of denoising on the ray tracing results. And so what I plan to actually do today after we do the basic material setup is shadows. So if you look at shadows right now, they are very this is very like Doom 3, you know, stencil shadows kind of look, because you have pixel perfect shadows. What I want to do is I want to have smooth shadows, soft shadows, but this needs, you can't really do this. The way you solve this without ray tracing is you do PCF or VSM or something like this, but with ray tracing you kind of have to do screen space filtering. And that breaks the kind of, all of these things force you in some way to go to a deferred like setup. Now we could have gone for a visibility buffer instead of deferred. Deferred is simpler for now. Visibility buffer is going to be like it's not going to be simpler. It might be a little faster, but it also might not be faster. It's complicated. So I'd rather essentially start going to deferred, which we did last time, and then separately explore what would have happened if we have gone for a visibility buffer. Anyway, okay, so now let's look at this stuff. First of all, I think we can just use diffuse factor here. And we can use material specular factor here. And then we can just multiply these by the texture fetch results if necessary. And then let's do the same thing for the emissive factor. Okay, and then let's do it like this for now. Okay, so the one thing you would notice is this color is very different, and I know this because I looked at some of this a little bit before off stream. So clearly we were just completely disregarding the colors. Oh, and there's one more problem. So we were just disregarding the information in the material file, which is like not correct. So the one thing is this is still not right, I believe. In GLTF there is this weird, not weird, but so like this color comes from the GLTF scene, and this color comes from the texture. However, this color is in linear space, and this color is in sRGB space, and we don't have correct sRGB sampling for textures, which we could do. Can we do this? It's painful to do this because you have to think about, you have to write a bunch of Vulkan code. I don't want to do this. I think I should have some helpers that kind of just fake gamma in my helper file. Yeah. So what I'm gonna do for now is I'm gonna just fix the yeah, I'm just gonna fix the gamma issues like using math in the shader. It's not quite correct. For example, right now we are sampling from a texture without using correct gamma correct filtering, which in some cases can be slightly important for like aliasing and stuff like this. But we're gonna ignore a lot of this stuff to the extent that we can. So this is linear, this is now also linear, so the final albedo is linear space, but then we should convert it to sRGB in the G buffer because the G buffer is 8-bit, this is more optimal, etc. From sRGB, oh, it's a math header. Okay, so you can see this color has changed. I think this is roughly correct. I don't know how the scene should look like, but it probably looks more correct than it used to. Okay, so now this second problem that we have is emissive, and the third problem is specular. So the issue with emissive is I've only reserved one channel for it, and this is where visibility buffer would have like made some of these concerns more trivial. But I've only reserved one channel for emissive, and I don't want to reserve more. Emissive doesn't feel like such a crucial effect that you spend the full channel on it. So I think what I want to do for now is encode emissive as like a multiplier on top of albedo or something like this, which is not ideal. Maybe you want to have a black object that emits lights or something like this, but I like doing things kind of one step at a time. So the one step at a time that we're going to take is we are going to take, let's see. Let's just do this. Let's take the brightness of albedo. This is not quite the correct constant, but it's like close enough. And then let's divide it by, wait, the other way around. Wait. Oh my god. My editor is fighting me. Wait. So let's take the emissive color and let's divide it by the, not color like the luminance. Oh, but emissive now is in, no, everything's correct. Everything is in linear space here. Actually, I don't recall which space the emissive texture itself is in GLTF. Let's ask this. It's probably sRGB. Yeah, okay. So emissive is sRGB in GLTF, so this should do this as well. And then, okay, what about specular glossiness? This window does not help now. I think this would be in extensions. I don't want to spend too much on the specular stuff because I want to change workflows in the future, but just out of curiosity. Where even is this? Oh, it's in archived. See, this is the problem. Like the bistro is using deprecated version of the extension. Okay. So specular glossiness texture. Okay, yeah, so this is sRGB as well. All right. So let's just do this. That's fine. So anyway, so I want to take the emissive color, convert it to luminance more or less. It's all kind of hacked, but you know, divided by albedo. In case albedo is 0, I don't want to get an N or something like this. And this is the emissive factor. So in the G buffer, I want to store the emissive factor. And then in our shading code, I want to reconstruct the emissive color, this guy, by multiplying albedo I should fix, we're gonna clean up sRGB stuff here in a moment. This is not great, but okay, I'm gonna just take albedo and multiply it by the emissive factor. Okay, and now the problem that we are going to run into, and we have just ran into here actually, is the emissive is supposed to make things brighter, but because we're storing a value from 0 to 1, it can only make things darker. Like it's an additive factor, but what you want to do is you want to have an ability for emissive to make objects significantly brighter than they are. There's a couple ways to solve this. So one silly way is we can just say, well, let's divide the factor when we are storing it in the G buffer by like some fixed constant, like 16. And then, hey, hello. Interesting. Is this just, this is over brightening that I get? So, okay, what if I do 8? Okay. What value was this lamp at? Oh no, okay, interesting. So this one, oh no, I don't know what color it was. Okay, yeah, so this lamp, interesting. I see. The other big problem that eventually we will solve is we don't have an HDR workflow. And so we'll have clipping in a bunch of places and stuff like this. But okay. Let's just go with something basic. Well, am I doing the right thing? I think I am doing the right thing because I'm dividing, yeah. It's just interesting that this lamp goes to white. I mean, it could make sense, but it just means the color was not pure, sort of. Oh, this is where sRGB math starts being important. Okay, let's quickly fix sRGB stuff. So our G buffer encoding is in sRGB. So we're gonna convert it back to linear. This stuff is fine, and then we are gonna compute our math, compute our like final color, and then we are going to convert, I guess here, it back to sRGB when we output. And I had some hacks in the shading to compensate for the fact that I don't have sRGB, so maybe this would be better. Oh, and this guy doesn't have math H either. So I need it here. Okay, okay. So things are more sensible now. Let's go back to the question of how should we encode emissive. So one option is to encode this as a fixed fraction. And there's this trade-off of how big of a range you want to have versus how sort of accurate, how much precision you want to have in the factor. And this thing is interesting because, oh no, okay, everything's fine. So this is how it looks without emissive at all. This is how it looks with emissive. I'm gonna keep this for now like this maybe. The thing you probably want is something different. For example, you might want to encode the emissive factor as like a logarithmic value. So you might want to do something like log 1 plus emissive f, which if the factor is 0, then it's logarithm of 1, which is 0, and otherwise it's like a power of 2. But then you probably want to rescale this to have more precision. But like if we do this, and then here we have something like this. Wait. Yeah, but you want to encode 0. Yeah, this doesn't. No, all good. It just should reverse this properly. Okay, so this is like another way to do this, but now this might be too. Oh no, but this is a range, right? So this is now a range of 0 to 1 that you can encode in log space, and so now you have to still like divide by 8, for example, and then multiply by 8 here, something like this. And this gives you, this looks similar to what it looked like with linear encoding, but it redistributes the precision a little bit. The other thing you might want to do is maybe you just have a fixed power function here with a fixed range. Anyway, there's like a ton of ways to encode this. I don't want to obsess too much over like what exactly this should be, especially because we don't have an HDR setup, we don't have, these emissive objects are very basic, so it's hard to know what will look best, etc. Let me just for now do logarithmic encoding, but I will, so this means we can do up to 256 times brighter than the original values, which is probably too much. Let's do like 32 times here. Okay, let's just keep it for now. This value should be exactly the same as this value. So ideally we would put it in some header somewhere, but we don't have a convenient header. So for now, we'll just hack it like this. Okay, so this is fine for now for the emissive, I feel, maybe. This is not obviously like, how do I put this? You can spend a ton of time on the optimal G buffer encoding and stuff. I don't want to spend this time. So for now, we'll just tweak things while they look good. Okay, so now let's talk about specular. So the specular, I wrote some code here, which is just like 4 lines to do very basic blin-fong. And if we enable this, we will get specular highlights. But of course, the problem is we are getting specular highlights from everywhere because we are ignoring any material properties for specular because we are not encoding them. And also we have horrible aliasing issues, so that's not great. And the problem that we have is that our G buffer doesn't have space anymore. But I don't want to increase the size of the G buffer, so I had helpers, which I added like off stream at some point, for octahedral encoding. This is just code I copy pasted from this paper. There's more efficient ways to do this that require 1 extra bit somewhere, and I don't want to spend this 1 extra bit, so I think this is fine for now. And what this can do is it can encode 2 float value in, like it can encode the direction, which is 3 floats, into just 2 floats from -1 to 1, I think. Yeah, and then you can decode them back. And the one thing to watch out for with all of this, which is not actually great for us even right now, which is interesting. Why is this not great? So we have, now that we added specular, we actually have minor precision issues even in the normal encoding. Oh, I wonder if this is the normal map compression, actually, not the... let's check what happens if we drop normal maps. Yeah, okay. So our normal maps are encoded using BC something, BC7 or something like this, which is okay for certain cases, but not optimal. If we remove that, then this highlight at least looks fine. This highlight looks a little sketchy. The other thing that we are doing right now is our vertices encode 8-bit normals, and ideally they should encode 10-bit normals or something like this. But all of this is stuff to figure out maybe later. And then we have some banding here. Okay, so the goal here, the goal today, I should have mentioned this, is not to get perfect rendering result for materials, is to just have more correct material representation of the scene, and then we can tweak this later. So, so instead of spending 3 channels on the normal, I want to spend just 2. So I think this should just be like this, because this goes from 3 floats to 2 floats, and it's still -1 to 1. So this will obviously break everything because I'm now encoding the gbuffer data differently. And the way this should look is okay. So this doesn't look like your typical normal data because it's this different octahedral format that only uses 2 channels. For example, here you can see that it flips from one the way this works is the sphere is divided into 2 halves, and then each half is unwrapped into an octahedral, sort of. And so there is a point of discontinuity where you flip from one type of encoding to another, and I assume this is that point. But then if we decode this back, which is we should do it a little carefully. So the value is from 0 to 1. So we decode it to -1, 1, decode the normal. And then this is the standard normal thing. So this, well, of course it's in linear space, so it's even weirder. But this is the deconstructed normal when we use that encoding. So now we can just move this thing here. And we should, in theory, have the original norm. Oh, no, without this, of course. Okay, so now this is basically the same image as before, but now we have the 3rd channel of the gbuffer, normal storage, or whatever that is, here. There's 2 zeros here, but we are using 10, 10, 10, 2 format for this. So this is a 2-bit value. So it's not super useful until we do until we store something like material index here. Oh, the other thing I should mention is, since I plan to do denoising in the future, we are going to try to do something very basic today, which is not full denoising. But for denoising to work well, you usually want a temporal component. For temporal, you usually want motion vectors. So I am guessing that in the future we'll have an extra gbuffer texture, which will also be 10, 10, 10, 2, with these guys used for motion vectors. It's kind of a necessity if you want to do anything temporal. And then this means we will have one more value in the gbuffer, which we can use for roughness or something, not roughness, metalness or something like this. But for now, we are operating on a shoestring budget. So let's try to figure out what we should do here. So the first thing that I'd like to do, so we have this problem, which is we have the specular color and the specular, the glossiness value. And what I planned to do in the past was to reconstruct metalness from specular color, just to not have to deal with 2 different workflows. But because I don't have space to store the metalness value, I think for now let's just encode glossiness and call it, unless I can somehow encode. It would be way easier if Bistro just came with metallic roughness workflow. Let me hack the specular, like the roughness basically, sort of, in, and then maybe this is okay for now. I guess you should call it smoothness, because I think usually the way people encode roughness is inverse. Is that true? I'm not sure. Okay, let's just, because we don't even have roughness, metal roughness assets, let's just encode the glossiness, which is the alpha channel, and let's just ignore, I'll leave it to do comment. Reconstruct metalness from specular texture. The issue again is we don't have space to store metalness factor, and I don't want to figure out encoding of two values in one float for now. So in gbuffer1 blue channel, we now have the gloss factor. Let's look at let's just do it like this. I want to look at what the value is, how it looks like. Yeah, so this is why, so you can see, for example, that the bike is highly glossy, I guess, but the bush is not, but we are not applying any values here. So obviously we have very aggressive specular highlights on these on this vegetation, which is not how things should work. You would notice that this is not, let me just add some more to do comments here. I just want to hack things into a decent shape for now. So maybe, let's see. Let's maybe start with this. Oh, is this GLSL, not? What? Hold on. Wait, I'm confused. Oh, right. And then the other problem is all of this stuff is not energy conserving. So, okay, let's do something very hacky for now. And then, why does... I'm so very confused. Why does lerp not compile? What? Does it not compile? It totally does not compile. Unfortunately, the way I've set up, yeah, okay. So this is the shader reloading in action, like it just compiles the shaders every second. So it now will just print the compiler error until I resolve it. So, okay, I am confused. What do you mean no valid overload? What? Oh, it's called mix in GLSL, yes? Yes, yes, of course it's called mix. Oh my god, this is what I get for not using GLSL much. There's no lerp function, there's only mix function. Fantastic. Okay, so this looks a little better. Again, all of this is not fully correct. This is not the correct BRDF that you should be using. But what I want to do here in the future is do a switch to actually metal roughness. For metal roughness, I think you have to transform the glossiness value a little bit to, like, there is formulas for converting between two workflows that are lossy but preserve enough information sort of for things to work reasonably well. But for now, I just don't want to over-engineer anything here. So this is decent, I would say. I don't recall what we do for the sky, or why this is the way this is. Okay, this is not too bad, actually. Okay, let me look at the kitten scene, which is, yeah, this is kind of what it is. Let me disable ray tracing. Right, here there's no specular highlight effectively, so yeah, that's fine. Okay, I am tempted to call this a good first step because things look more correct now, and this is closer to what I wanted to do for the previous stream where we did materials. We just kind of ran out of time. The normal encoding on the normal map clearly sucks, so I'm not sure why that is, because I think I'm using the original textures. Yeah, like you can see the normal map quality here is just not great. So that's worth looking into in the future. BC7 is not the ideal format for normal maps, but if I only have the original textures, then I can't re-encode them to improve quality. Okay, let's commit this for now, because this is better than it used to be. The normal quality is unfortunate because it's going to make it difficult to distinguish artifacts from my gbuffer hacks from artifacts from like normal encoding. Oops, reload. Yeah, so see, if you disable normal maps, then things are still not great here. There's still some banding, but I think this is because it's for different reason. Oh, one thing I wanted to do actually is I had this thing saved here. So let's call it like this. So one thing that you end up having to do in a lot of cases when in general, we are going to start relying more and more on noise in this render, maybe is a good way to put this, than we used to. And the basic thing that you want to do, and I'm wondering if some of this is just that, some of the banding. I'm not even sure if you can see banding on video, and if you can distinguish the artifacts of video encoding from the artifacts that I'm seeing. But one thing that you want to do is you want to do a little bit of denoise, a little bit of noise, like you want to introduce a little bit of noise into your image and keep that noise under the quantization threshold so that the banding gets like less visible, and this is it's just good practice in some sense. So I'm just wondering if I just do gradient noise UV. Let me just look at this value first. Hold on. Okay, so clearly this is not right. Maybe fit position. Okay, so this is barrier noise, I think, or something like this. It's called. And if I divide it by 255, then this adds a value. I should probably do like this times 2 minus 1 over 128 maybe. Oh, wait. What? Hold on. Oh, no, yeah, all good. All good. Over 256. Yeah, this particular banding is not that. This particular banding is probably some sort of specular highlight banding or something like this. I'm gonna leave this particular hack here for now, because I know in some cases it improves the banding that I've tested before, but this one is just... Oh, the other thing I don't know actually is there could be all sorts of... Well, this just looks like specular banding to me. So this would be either from the specular power quantization, which we can eliminate by doing this. Then this might just be the remaining normal artifacts. I actually am wondering what happens. Oh, one thing I might want to do is I might want to do this for extra precision. No, but the one thing I'm wondering though is what happens if I deband to normal. How do I do that? Wait a moment. Things are very slow when you resize the window in Wayland, unfortunately. Okay, yeah, none of this actually helps, which is weird. Interesting. This is just broken in the sense that... Okay, no. Interesting. All right, you know what? I don't want to endlessly debug quantization noise because this could be a whole stream of its own. Let me just leave this here because I wanted to do this before. And let me undo all of the other hacks that I was doing. So we preserve spec gloss, we preserve things here. Okay. This is fine, this is fine. Okay, this is actually, maybe let's call it good enough for the material portion for now, because again, there's now specular highlights, the emissive works better, the specular is material dependent now, and the colors are preserved. And so this puts us in a better place. But to be clear, this BRDF is very, very incorrect. So I'm just gonna leave it to do comment here. This is very this is not the correct, this is not the BRDF we want. And ideally, you know, all of this needs to be like reworked separately. And I want to re-enable shadows because I disabled them. Oh, we segfaulted when reloading shaders for some reason, I guess. Interesting. All right, whatever. Shady reloading is not completely stable. It's fine. Okay, so I think I'm tempted to call the material portion of the stream in a, like, not done, but like it's in a decent enough spot, because I really want to look a little bit more into shadows and rework a little bit how they are integrated, so then we can do more interesting things with them than just cast a single ray. So let me commit this. I'll look in chat because I've been ignoring chat for a while now, and then we will see what we can do. better material integration. So material data is now in a separate buffer so that extra material parameters do not bloat mesh draw structure, which regresses culling rendering performance when we have lots of draw calls. We don't have draw calls, but you know, mesh objects, I guess. And then integrate, we now preserve various material related factors from GLTF data and integrate them into shading a little better with more sRGB correct results and nicer specular. We will need to rework BRDF integration completely in the future, ideally switching to metal roughness GGX at L. And also there is some normal banding issues that remain that we should investigate. And again, normal banding is difficult to, you have to like, one thing that is easy, for example, to try is, what happens if we increase the precision of the normal data that we store in the vertices? And this might help in some cases. But doing that requires tweaking C++ code a little bit, which I just don't want to spend time on. And again, because of the normal map artifacts, like the most objectionable artifact right now in the real scene is the normal map encoding. Like all of this garbage is the normal map data being bad. And the normal map data being bad requires re-encoding textures from a higher resolution source or higher precision source, which I don't have. So everything else that we are doing wrong is like less bad than this. Oh, actually, am I using original textures or am I using re-encoded textures? Oh, I see how it is. One moment. Hello. Okay, why did I do that? All right, this is maybe my mistake. I re-encoded, so that makes more sense. I re-encoded the textures using etcpack. etcpack is fast, but it doesn't guarantee good results. So let's disable that, and then let's look at this again. Well, this is still pretty bad. It's different now, maybe, but still pretty bad. So maybe the original textures are just, yeah. Maybe the original textures are just not encoded very carefully. And so the normal data is a little bit messed up. But we can't fix this because we don't have, I feel like the original Bistro asset had DDS textures with BC7 as well. Let's ignore this for now. We might come back to this at some point in the future, but it's difficult to fix a scene that you have been given the compressed version of. So maybe that's what it is. All right, so let me look at this. I don't really know. You'll have to ask this to a Roblox rendering engineer. I don't recall details around PBR implementation in Roblox, so I don't really know. Yeah, so LSing, TA. So I feel like I basically covered the aliasing stuff. So here's the problem. Here's the problem. TA is a scary proposition. There's a lot of issues with this, but let's look at what we have right now. Let me just move the camera. I don't know how well this comes over on video, but there's a ton of specular aliasing right now. Now, specular aliasing is actually something I want to look into to see if we can fix it separately, because there's techniques to combat specular aliasing that are stronger than whatever temporal filtering you might have to do. So it's tempting to think, oh, hey, we can fix the specular aliasing. Okay, so let's disable specular. This is why I added, this is part of why I added camera movement, to be able to assess this better. So let's kill specular completely. Reload the shaders. Okay, so there's no specular anymore. So again, I don't know if you can see this at all, but the far away portions of the scene, when I'm moving the camera, they still alias like crazy. So that's like bad. That's not acceptable. And I should note, this is a 4K. Okay, you're seeing the stream in like 1080p or 1440p or whatever, but I see aliasing on my display. My display is 32 inches, and I'm using 4K resolution when rendering into it. Which is to say, you can't increase the resolution anymore. It's already too much. And because it's 4K, even multi-sample anti-aliasing is a scary proposition at 4K, because it's an insane amount of just data that you are pumping through. Plus, the G-buffer setup and the deferred setup and the ray tracing and all of this makes multi-sample anti-aliasing also difficult to do, right? So I want to fix these aliasing issues, and it feels like the only clean way, relatively clean way, to fix them for geometry in the distance is to do TA or something like this. I don't love that because, you know, there is artifacts that TA comes with that are difficult to fix. But this is what I want to do in the future. Having said this, there is a problem with TA. That's a fundamental conflict of goals with this stream. As you've been noticing, maybe, we have been trying to do things. We have been trying to minimize the amount of time we spend on things and maximize the output that you get out of things. So what I just did, for example, is I just hacked some BRDF stuff together. If you're doing a production PBR implementation, you're doing a ton of paper research, then you're doing a lot of experimentations of like optimal encodings and stuff, and then you get like a better result than what we have right now, obviously. But I don't want to spend inordinate amount of time working on all of this. TA is a terrible problem. TA, you can have an engineer spend like a year full-time literally on TA, because there's performance and correctness issues around this that are difficult to resolve. There's some off-the-shelf implementations. For example, FSR2 has basically a TA implementation inside it. But that means taking a bunch of code that some other people wrote that we don't know much about and integrating this into the renderer. And I said many years ago about this renderer that is going to be a from-scratch renderer. And so I don't know how to resolve these two. On one hand, I should be writing my own TA implementation. On the other hand, I just worry that it will take an infinite amount of hours to get good results. So I haven't decided yet. And I have the same issue with shadows, which I'm also not sure what to do about in that sense, which I'm going to talk about in a second, because we will need to, I want to do a little bit more shadow rendering on stream today. Yeah, see, the problem is you can't just add TA. You like add TA and then spend an eternity fixing artifacts. Now, the good thing about our current setup is we don't have objects moving. We can move an object. Any object right now in the scene can be moved. It's just we don't have code to do that. Because of this, technically, we could, you know, just implement TA, and then TA on a static scene with slow-moving camera should actually be really good. So because of this, maybe the correct solution here is to implement TA ourselves and then, you know, ignore the artifacts for now. We'll see. But the bigger issue than geometry aliasing that we have is the shadow problem. So let me talk about the shadow problem. And we'll try to write some code to start tackling this. It's impossible to solve shadow rendering in a single stream, so we will not be able to do that. But so here's what I want. Sorry, somebody asked about magic numbers in the hashing function. You'll have to read this presentation. The short story is there's a ton of different hashing functions that have different properties on GPUs. We'll actually need another noise function for what we are about to do. But maybe I can just use this one. This only gives me one value and I need two. That's unfortunate. Ideally, I need to. This is a deep rabbit hole. I spent a little bit of time last week looking into this, and there's so many hash functions with so many properties. If you haven't, so there's a new book released, GPU Zen 3. You can buy it on Amazon for $3. You get a virtual version, like a Kindle version, but you can open it in a Kindle app on, if you have a tablet like an iPad or Android tablet. This book is worth $3 for sure. And in particular, it has a very long and very good article on Cyberpunk and how they integrated ray tracing, basically. And I was reading this, and this was interesting because a lot of the things that they ended up doing don't look too different from what we are about to do, from what we have been doing. They have like a G buffer, it's pretty compact. They're doing ray tracing. They have to do denoising with various denoisers, stuff like this. So I think in some sense, my plan is almost to replicate some of the things that they have been doing, but keep it much, much simpler and more contained. But one fun thing that they have there is they use xxhash 32 to generate a hash value for the pixels, because you need a noise function to do to like jitter rays so that you can get better results with fewer rays. And so they use xxhash, which I didn't know people use it ever on the GPU. I thought of it as a CPU side hashing function, but apparently they just ran it on GPU and they liked the results more than others. So yeah, this is like these specific numbers. I think this noise is specifically either Bayer or something like this. And so these numbers presumably have some actual meaning behind them. I'm not sure, but also they are tuned. I had to feed the pixel position into this, so they are tuned for some specific like grid size or something like this. But yeah, I don't know fully well the origin. You'll have to look at the paper. All right, so. But yeah, so here's the problem with ray tracing. And I talked about this last time already. So we have the ray trace. We are running at 4.5 milliseconds on 4K. This is using official MD driver. So it's not too bad, but our shadows look like stencil shadows, which is not the worst thing in the world, but this is not how they should look like. And what I want them to look like is like soft shadows. Traditionally in computer graphics, the way you do soft shadows with rasterization is you do shadow maps and then you have a filter kernel and you blur them and stuff like this, or maybe you blur them in screen space. Ray tracing allows you to do an interesting thing. So we have this code right now. And let me just hack this a little bit to show what I mean, but I want to rework this. We are going to rework this code in a moment. But so we have this sun direction, this direction towards the sun, I should say. And so from every pixel, we shoot a ray in the exact same direction. And that's the sun direction, right? And then we trace the ray, we get the result, etc. here's the thing you can do. I'm gonna try to. I really need a different noise function. Let me. I had some hacks here. Somewhere. Oh yeah. So let me just take this as is. I need to. There's a lot of different ways to do noise that have different properties, so I really don't want to focus on this too much. But let me. Oh, actually, you know what? Let's just use this gradient noise thingy, and then we'll just call this again here. It's fine. Okay. So let's say we took the direction of the ray that we are casting, and let's say we change the z value of that direction a little bit. I want to do this in a way that randomly changes it in both directions, and then does this like in a sort of small way. And let's see what happens. So this is not too bad, actually. Maybe we will just go with that noise function. Okay, so I don't know how well you can see this on the screen, especially because it's like screen space, so I can't even zoom in to show you the results better. But the shadows are blurrier. But there's an interesting property of shadows, and this is more difficult to get with rasterization and ray tracing. So if you look at this object, I think, yeah, let me yeah, so I've expanded the random offset a little bit. So I don't know how well you can see this on the screen, on the video feed, but if you look here, you will see that the shadow barely changed at all. But if you look here, you see that the shadow got noisier. It sort of got softer in the sense that if you look at this from the distance, it actually looks pretty nice because you can't really see the obvious noise pattern. But if you look at this from a closer distance, it doesn't look like as pleasing. But what's happening here is that for pixels that are close to the geometry that is occluding them, the extra small random delta that you apply to the direction doesn't affect the trace result too much, because you're going to hit the geometry no matter what. Like for this pixel, pixel next to it maybe shifts the ray a little bit, but it's still sort of more, it's still likely to hit the same object. But for pixels that are far away from the occluder, this random offset changes the ray direction a little bit. And the further the ray travels, the further the distance is sort of between the points on the original ray and the points on the randomized, on the ray with a random offset. What this means is that objects further away from the thing that they're occluded by get more noise in the shadow output, which is basically what you want to get correctly sort of softened shadows, because the actual way that soft shadows work in real life is the sun is not a point, the sun is like a sphere or like a ball, like somewhere very, very far away, and the rays to the sun, they don't go in one direction, they go in slightly different directions based on the kind of point of the sun that you're looking at, and what you see in reality is like an average kind of all of these. And so basically on the border of shadows you have this penumbra, and the size of this penumbra should vary based on how far the occluder is from the pixel. So we just got here, we just changed a couple lines, and I don't even think it will change the performance too much. Let's see. So we are spending right now 2.03 milliseconds in this half screen resolution to trace the rays with this adjustment. Let's disable this. So now we are spending 1.85, right? So we are paying like 10% cost for essentially more noise in our rays, which makes the ray tracing functionality in hardware less kind of efficient. But just 10% for like a decently soft shadow output is way better than what you get out from shadow maps. So the base cost for ray tracing is very high in our renderer, but what we get for this is ability to get nicer looking picture with less incremental cost. So this actually by itself doesn't look too terribly, but again, there's all of these, well, there's two problems. So one is we are only shifting, this is like not the correct way, obviously, to tweak your ray direction. The correct way to tweak the ray direction is this. You have a point, and then instead of a ray towards the sun, because sun is not a point, you have a cone. And what you want is you want to sample a random direction in that cone and then trace that. And the way you sample random direction in that cone is you have some way to produce two random numbers instead of just one random number. And then you like do a little bit of math to convert from the right coordinate to the right coordinate space and stuff like this. I don't want to do the full correct cone math today, to be clear, but I do want two random numbers. It's annoying that, and like you kind of want two uncorrelated random numbers, and because of this I was looking into various hashing functions. So I'm not sure how to best hack this together, but I do wonder if maybe I can just hack this like this. But then the other issue is, oh yeah, okay. Let's see what happens if I just do something very stupid. Again, this is not the correct way to do this. Unfortunately, it's hard to know if I am making things better or worse. How do I... Let me look at the noise output. So what you actually do, there's like papers on this with a large number of noise functions that you can look at and pick the one with the properties that you like and call it a day. So this is the raw noise output with two channels, red and green. And it doesn't look, you can see patterns in this data, but there is some complicated questions around noise. There are certain cases where you want noise where you see no visible patterns in the data, and there are certain cases where you want noise that has patterns in the data that are predictable, because when you apply a denoiser on top of the noise, in some cases you want the denoiser to be able to give you a more stable image as an output. And sort of having some amount of patterns in the data helps. Let me just go with this. I don't want to like find a new extra noise. If I'm doing something very stupid and I should be doing something much smarter, please let me know, because I'm not like an expert in this. And I don't like some of, am I even doing, hold on. This is the more correct way to do this. Okay, all right, this looks better. Again, then the correct thing to, well, this doesn't look very good. The correct thing to jitter all of this is to do a random cone sampling, which is emphatically not this. But I don't want to do the correct thing because it's too fiddly. As with the BRDF stuff, I want to set up basic kind of framework for improving this in the future, and then we will actually improve this in the future if we need to. But again, this is not too bad. Yeah, I'm just worried about the correlation problems with this noise. Oh, okay. So this is probably really bad. Like, you probably shouldn't be doing what I'm doing right now, but let me actually just keep that for now. So the actual real problem, though, is in addition to the correlation issues that I actually see when I move the camera, the real issue is you see the noise. So like after you introduce the noise, what you have to do is you have to remove the noise from an image. And you remove the noise from an image by denoising it. And denoising is a form of denoising that can work okay for shadows is blurring. And because I don't want to do the full denoiser and stuff like this, because this is another giant rabbit hole, I just want to blur all of this to bits. And the hope is that that something fairly simple from the blurring perspective will be enough to hide the extra noise that we're introducing into the image. And then through some combination of improving the noise and improving the denoiser, you can arrive at good output without sort of without sort of breaking the bank on performance. Because real shadow denoisers are complicated, they're multipass, they have to have ray intersection timestamp to actually do a filter kernel that, the intuition for, I guess, would be this. If you're looking at these pixels, for a denoiser to do a good job, it has to look at the pixels in a wide radius, because you're looking at an area that's in a penumbra that's fairly wide. But if you're looking at like this pixel, then you almost don't need to denoise it at all. It's already noise free because it just sampled almost the same data in neighboring pixels. And so because of this, when people do shadow denoisers for real, they incorporate the distance to the occluder. And we can get, we don't have it yet, we can get the distance to the occluder because ray tracing functionality gives you that almost for free, except that you have to switch the ray flags. This is something I didn't really talk about last time, but or 2 times ago, whatever, but we are using this special mode that says we don't care which object you hit, as long as the ray hits any object, return me the result. If you want the distance to the object, you have to remove this flag and switch to the default behavior. The default behavior is you get the closest object. The problem is this has a performance cost. So right now, for example, we are spending 1.7 milliseconds on the ray tracing. If I just disable this 1 bit, we are now up to 2.44. So that's 0.7. It's almost a 50% higher cost. Not quite, like it's a 40% higher cost, right? So I don't want to do all of this yet because it requires complicated reasoning and complicated code and stuff like this. But what I do want to do is I want to blur all of this. But for me to blur all of this, we have to move shadows into like a separate pass so that we can have a pass that computes shadows, then we can have a pass that blurs shadows, and then we can have a pass that actually applies shadows, which is our main sort of shading pass. Which is also good because then we can just disable shadows, or we can do shadows at a low resolution, or we can have more, because shadows are actually the bulk cost of our shading right now. We want to gain more freedom on reworking this, denoising this, doing low resolution and stuff like this. So that is what I am going to do next. Hopefully I will be able to fairly quickly do this split pass plus some blurring that doesn't look too horrible, and then that's kind of going to be the stream today. I'm just going to keep this here actually for now. Okay, so to be able to do this, we need to move the ray tracing code into a separate shader. Let me look at whether it is insightful. The code editor is ZED. Yeah, so basic TAA shouldn't be too bad. The real issue, I think, is tuning TAA to fix all of the disocclusioning issues and stuff like this. But the other thing I want to do is I want to maximize the amount of reuse I get from the code that I write. For example, we'll have to do denoising for shadows, and we'll also need TAA for geometry anti-aliasing. And if they can be more similar, it's not the same code for various reasons, but maybe they could be more similar, I'm not sure. Anyway, whatever. TA is a separate story, but yeah, I think we'll have to do TA because I don't like aliasing, and the current aliasing that we are getting is too much. Even MSA, unfortunately, is not perfect. Even MSA 4x, which is very steep cost for a 4K renderer, especially with G-buffer and stuff, is not fully hiding the artifacts in the distance. So, anyway. You get a small amount of coordinate hardening from the sun, but you do get it. And I think depending on if there is like clouds in front of the sky, like a thin layer of clouds, then the rays get refracted much more. And so I think in practice, you can have both hard shadows if the sun is like in zenith and the atmosphere, like the sky is very clear, but you can also have very, very soft shadows depending on stuff. Shadow bokeh? I'm not sure what you mean by shadow bokeh, but maybe you mean the same thing. Because it's kind of, the way bokeh works is kind of sort of similar, like the rays get distorted a little bit because the lens is not infinitely small. So maybe you mean the same thing. Yeah, hopefully the answer is yes. All right, so let's just do this and see where this takes us. The one thing I want is I want to record the frame. Maybe this is fine. Oh, I should say the other weird property of noise that you have to grapple with is, so if the image is still. So right now, for example, this still image, there is a little bit of noise that you see here, but if we blur this or denoise it, it's going to be fine. The problem is that if I move the camera like here in this region, I see both the patterns in the noise, but also I see shimmering in the noise. And this is because the noise that I'm applying right now is screen space. There's other ways to derive noise from. For example, one thing that we actually can do is we have the world position of the pixel. And so what we could do is we could say, oh, take the world position like XZ or something like this. And derive our noise function from that. Oh, I should have done a shaded reload. And this looks horrible because of the scaling that the world position has. But I think if I, oh, come on, if I like multiply, yeah, if I multiply this by some large value, let's call this 10, and then I multiply by this by an even larger value. Yeah, and then I multiply. There is correct ways to derive this. This is not the correct way to derive this. All right. Yeah. So if you do something, I was hoping essentially eventually that I can do, initially, that I can do noise based on some value that is more stable. Screen space is not ideal because as you turn, screen space is not ideal for two reasons. One is you turn the camera and the noise pattern kind of turns with the camera because it's the same in every pixel. But then the second problem is that you move the camera a little bit and the noise computed in every pixel changes drastically because it's in a completely different place. And I was hoping that there's some way to do a more camera motion stable noise so that the temporal jitter in shadows is less severe, but I didn't find anything obvious there. So maybe this is just, maybe people just do screen space stuff, I'm not sure. The other thing I should note is a lot of people do blue noise, dithering, blue noise sort of noise, I guess. Blue noise, you have to bind like a texture, usually that's pre-computed to be able to do blue noise. So I'm trying to favor techniques that are very quick to experiment with. but people who actually have done noise for real in their professional graphics career probably are looking at all of this and say, oh my god, all of this is terribly wrong because things should not be like this, which is fine. Anyway, so yeah, the reason why I mentioned this is I'm worried that even the blur will not hide the movement of the noise pattern very effectively, but we will see. So the first step is I need a separate shader. Let's call it shadow or something like this. And essentially the job of this shader is going to be just do the shadow casting portion. So it's always going to be using ray tracing, because if you're not using ray tracing, then we don't have a way to cast shadows, obviously. So it will need TLAS, it will still need, I will bind all of the same stuff. I guess we won't really need the G buffer, but there might be cases in the future where you need the G buffer and do something funky with the rays. For example, if we ever get to reflections, which is its whole separate kind of worms, the way you do reflection is you trace a few rays, but you jitter them based on the roughness. And so for something like this, you'll need the G buffer data to get the roughness from. But for now, let's do something fairly simple. Why did this even start at... Oh yes, okay, cool. So I just want to move the shadow casting code to like split the shadow casting code from the actual G buffer shading code. So we don't need all of this stuff. We do need clip because we need to cast the rays. We'll get shadow, and then we'll store the shadow value in the output texture. And we will do the same like denoise thing here. So, and then in our actual shading code, we will stop doing anything ray tracing related for now. So I have to regen, CMake projects, okay. And then if I just run this, then what will happen is we just don't have shadows, obviously. So I need to fix this. Let me switch back to debug. And the reason I'm switching back and forth between debug and release is I have validation layers in... Maybe I should like fix this. I don't want to do too many things at once. I have validation layers automatically enabled in debug, but release runs faster for loading the data. And so when I iterate on shaders, I run it in release. But actually, we can probably just enable validation layers in the release under a separate like configuration thing. I will probably do this later off stream because it streamlines the workflow. Okay, so the way this will work is this. The way this must work, I should say, is this. So we have the G buffer and the depth target, but we'll need two more textures. One is we'll need the texture that we render the shadows to, and the other texture is the other texture we will need is we'll need the texture where we will blur the shadow into. You basically can't blur in place as far as I know, so let's just call it shadow blur. Or let's just, it's fine, whatever. Whatever the names are, they're fine. So then we probably should come up with a better system for this, but we will need to recreate all of these textures when the screen resolution changes, of course. Oh, but the nice thing about doing this is that in the future, we could shrink the shadow target and do raycast at low resolution, but I don't want to do this today. So we will destroy them with shadow target image. We will destroy them if necessary, and then we will recreate them. So the shadow target, can I do? Okay, I will start with the, there's no reason why I can't do R8, right? Maybe you want slightly more precision, but that seems a little excessive, right? Yeah, you know what? I'm planning to work with all of this in compute, but I don't think there's the reason why I can't just try to an 8-bit image in compute. So let's go with this for now. Unlike the G-buffer, we want an ability to write to this image from compute. Oh my god. So yeah, let's just go with this. So shadow target and shadow blur target, the same thing. And then at the end of it all, we need to destroy these. So then, in addition, or when we have our shading pipeline working. Oh, this is actually pretty cool because we can now disable. So previously ray tracing supported. Previously we couldn't like do the final G-buffer thing if the device didn't have ray tracing, but now we are planning to separate this from we're separating shadows from shading, if that makes sense. So that's gonna make the code a little bit easier to work with because we'll support some stuff that we didn't support before. So that is cool. All right, so let me and then I guess we won't really need, I'll keep the blit for now. Okay, so for now, let's do the minimum amount of changes that we need to support this extra pipelines and stuff. And then we will need the blurring pipeline, but let's cross one bridge at a time. Yeah, let's cross one bridge at a time. Okay, so we will take the compute shader and we'll just run it before the actual shading pass. And then we will later rework the C++ code so that we can do that independently. Let's, to avoid weird complications, I'm going to refactor this like in a moment. So bind the shadow pipeline, and then we will output to shadow target. Wait. Yeah. Oh, shadow target image view. Okay. And then we will not need the G buffer for now, but we will need the depth buffer and we will need TLAS. So then we will do shadow program. And then we'll keep the struct for now because it has some of the data that we'll need. So this is shadow program. Okay, we will also need a barrier, so the validation layers will not be happy with us right now, but we will fix that separately. I just don't want to mess up the descriptors, so I want to be a little bit careful about this. This is, yeah, so we will have to bind, instead of TLAS, which we no longer need, we will bind shadow target, and in future it's going to be shadow blur target, but all right, and then we will need a barrier. I'm not sure if we'll need a barrier. Well, yeah, we'll need two barriers. So oh boy. Barrier code every time is painful. So to avoid having to deal with this mess for now, I'm gonna keep this in general. And then I will need to transition. I will need a barrier to set up like a dependency, because I'm going to be writing to the shadow target from compute, and then I'm going to be reading to it from compute. And you need a barrier between these to like enforce synchronization. So this is not optional, unfortunately. And the other thing that's unfortunately not optional is you need like an initial transition, I think. Okay. This probably does not work, but let's see how this doesn't work. I'm expecting to get like validation complaints. Oh, I didn't even enable sync validation, which is a mistake. Oh, so I'm sure these barriers are not quite correct, but I have synchronization validation disabled, so we can't establish that for sure. Let's sample from the shadow texture to actually be able to know if it works or not. Okay, so I'm very sure the barriers have some bugs in them, because barriers always have bugs in them. Oh, the one thing I'm wondering is, has the performance changed at all of the final like pass? Let's see. It has a little bit. Maybe. So we might have lost a little bit of performance, like 50 microseconds or something like this, which is fine. I don't care about things like this for now, because the performance characteristics of all of this code are going to change dramatically. So I will accept this for now. I'm sure the barriers are wrong. I want to fix this, but before I fix this, I need to... This bulletin code is kind of annoying now. Oh, but if I don't render the shadows, then I will have to clear the texture so that I can actually sample from it or something like this, which is also going to be done. Okay, for now we will keep the property of our render, which is that if you don't have ray tracing, you get nothing. This is now more fixable than it used to be, but I don't want to fix it quite yet. So then I guess I should fix the validation. No, let's run a compute dispatch that pretends that it blurs shadows but doesn't actually blur them. And then we will actually be able to talk about blurring. So then I want yet another shader. Shadow comp, shaders, shadow blur. So there's a couple complications with blurring, but I want to do the simplest possible thing today. And then if we need to do something else in the future, we will do something else in the future. So for now, our beautiful shading code is just gonna sample. Yeah, this is fine for now. It's gonna sample this and then just copy the result back to the output. All right, and then here we'll need essentially one more block of code exactly like this, which is gonna bind the blur pipeline, which we don't have yet, and then bind the shadow target as an input, but then we also need the output. Oh, right, so shadow So we need shadow blur target as an output. And then we will need shadow target as an input. So I want a sampler there. You don't need a sampler, but I haven't. There's some SPIR-V issues that I had to work around at some point. So in theory, when you read from textures without any sampling, you can just bind them. But I had to fix some SPIR-V stuff for this, and I've been procrastinating on doing that. So we will not do this for now. And then okay, and then we will need one more barrier, which is we'll take the shadow blur target and then we'll do the same dance. And then we will take the blurred texture. I don't know why I'm capitalizing blur in some cases and not capitalizing blur in others. I guess I should uncapitalize this guy. For consistency. Okay, so we'll need one more pipeline. Yeah. We are starting to get too many shaders, so it would make sense to automate some of the boilerplate that I'm writing, but not yet. Not yet. Okay. Oh, I need to make. Okay. Shadow blur. Oh yeah. Hold on. Shadow blur barriers. And the other thing that I might need to start doing at some point is automate the barrier stuff, because that also is getting annoying. Oh no, wait, not here. Hold on. But doing correct. So like, there's a few ways to automate the manual work that I'm doing with barriers. One way is to implement a render graph. There's some other ways that are a little bit lighter weight, but have some other pros and some pros and cons basically. So I haven't figured out what I wanna do yet. But okay, so we render to the shadow map. Not sure why there's a warning here. It's kind of weird. Okay. Why is there a warning here? That makes no sense at all. Okay. So then when I have rendered to the shadow map, to the shadow target, I should transition it to read, but then the blur target, I should transition from nothing to the state where I'm gonna write to it. And then we will write to the blur, then we'll transition the blur. Okay, this is probably correct-ish. Well, clearly, and this is not correct. Let me see. Did I bind stuff here in the right order? Blur, I did not. Now I did. Okay, so this is the exact same code. We've lost like an extra 20 microseconds or so, but we will do blurring, and you know, we will lose even more, which is fine. So let me check if I have synchronization problems, which I might, because I kind of just blindly changed the barrier code. Not blindly, but you always miss things. If you work with Vulkan code, you have to use synchronization validation. Okay, things are correct, hopefully. Because without it, you will have bugs that you don't know you have, but you have to enable it. It's like a separate layer. I covered this at some point in the stream series, I'm sure. So now what we have is we have a compute shader that has access to the shadow image that has all of this noise. And what we'd like to do is we'd like to remove that noise. How do we do that? There's a few different options for how to do this. And in some cases, you want to have two different compute shaders because you want to do it horizontally and vertically. But the big thing that I want to do, and the reason why I even have the depth image here, oh, will I need Xenia or something like this, maybe we'll see. I may have to change some of this code later in more ways. But the one thing that you can do, which is very straightforward and simple, is something like this. Let's just say we want, let's just call it a 5 by 5. So let's just say we want to iterate from -2 to 2 along both x and y, and then we will fetch the texture from uv plus vec2 xy over image size, and then we'll divide shadow by 25 because we've just done 25 samples, like 5 by 5, and just call it a day. I should switch back to release again because that should have worked. Interesting, right? Let me, okay, hold on. So I went too fast, and as usual, I paid for it. Let me keep the original code, and then let me do the define blur 1 or 0 or whatever, and then we will start doing shader reloading probably. Okay, so what the heck? Wait, what? I am confused. Did I get the indices wrong or something? No. Oh my God, of course I did. Ah, okay. All right. Okay. Okay, perfect. Okay. Things work. Typos are the worst. So, I don't know if you can see at all what's happening, but things are getting a little softer, and some of the noise, actually most of the lower frequency noise, I think is being removed. So if you look at this thing, I don't know to what extent the video compression just kills all of this and you just don't see anything changing, but definitely the blurring works. the problem, or part of the problem, is I guess the blurring is just not wide enough, because here it breaks the pattern, or like it blurs across the yeah, it smooths out the high frequency noise, but the noise also has low frequency components in it. I'm now wondering, it now matters what these constants were in the gradient noise. This is kind of the thing I was talking about, where if you had the distance to the occluder, you could estimate how wide the filter kernel should be and stuff like this. We don't have the distance to the occluder. What we do have is we have a fixed noise pattern, which is here. And this is interesting because it's fairly wide. It's fairly wide. Whatever is the 1 over this value is the like fraction. So this is 15. Oh, the other one is 171. Is this like a typo? I don't want this. Hold on. Okay. Now it's more periodic in a visible way. But at least it's like around 15 by 15. 15 is a lot of pixels to blur over. So, but okay. Let's do... Yeah, it's fine. All right, so if it's a 15, yeah, okay. This is expensive, but we will think about this a little later. So what is going on? When you apply jitter, you get different pixels that have kind of different results. But if you know kind of what you want is, you want an ability to take the blurred result or the jittered result and then apply the blur to it and then hide the consequences of the jitter correctly. But if the jitter period is very large, then in areas with wide penumbra, you might have pixels that are kind of far away that sort of belong to the same penumbra, if that makes sense. And I guess, yeah, and I'm not sure if the period of the noise should exactly match the blur width, or if there is like some 2x relationship or whatever. We can just tweak this value until things are good enough. But so we started with we started with 2 by 2 or 5 by 5. This is like the actual width of the kernel is this times 2 plus 1. So this is not enough. And again, I don't know if you can see this on the video recording, but you can still see significant artifacts from the noise. The blurring doesn't like remove them completely. In a sense, it looks, well, it looks pretty objectionable no matter what. But the issue is the filter, the noise like repeated every 17 pixels or so, give or take, in every direction. And so if you only look at an individual 4x4 or 5x5 region, of course, you will not be able to fully smooth it out. I don't know if there is an intermediate value that's like decent for now. Even with this, I can see, you can probably not see anymore, but I can easily see objectionable patterns. In motion, things still suck, but okay. Let's go with this for a second. This is really expensive, but there is a reason why I'm doing things like this. Now, there's a question of how expensive is this really? Yeah, so this is very expensive. This like doubles the shadow cost. Damn it. Let's go less aggressive on the jitter, I guess. And then less aggressive on the noise and see if things still... I don't think this is quite the relationship that is going on here. Yeah, all of this sucks. Now, this is like a bad way to implement standard ghosting blur for a couple of reasons. One is we are not efficiently utilizing the texture sampling hardware. We could be getting a 2x2 sample for almost free by sampling in between pixels, and we are sampling the center of pixels. And then, of course, with a filter kernel of 5, so this is half of the width. So this is like an 11 by 11 filter, and so this is like 100 samples, 121. And what you actually want to do is you want to do them horizontally and then vertically. The reason why I didn't want to just do it like this, though, is going to be hard to show, maybe. But, well, no, it's actually pretty easy to show. Yeah. So the problem, there's kind of two problems. There's a few problems. So one is, if the filter is too small, then we see a lot of artifacts, especially in motion. If the filter is large enough, then I'm assuming they are hidden. Still not even hidden with 10. It's kind of crazy. Is this double there? Is this a Nyquist limit? No, even that doesn't fully work. Okay, interesting. I would need to think about what the correct ratios of all of these things are. But the one big issue, in addition to the jitter artifacts, is that if we just blur it like this, then you see significant issues on the boundaries of objects. And what's happening here is that these pixels that are not on this menu, like in front of the camera, when we blur them, they average things to the left of them and things to the right of them. This is a natural artifact of screen space filters, and the way to fix this is to use bilateral filters, so where you take the depth information and based on the delta between depth values in different pixels, you kind of take the results or not take the results. Let me take less aggressive filter width for now. Even this is crazy, honestly. So the issue is usually the way you implement fast filters is you do them in two passes, horizontal and vertical. The problem is that when you start doing bilateral filters, they split into two passes becomes incorrect. But I feel like we don't really have a choice here because we need a fairly wide filter. So the filter right now costs a millisecond at this non-4K resolution, which is actually more than the ray traced results, more than ray tracing. We've managed to make things slower than ray tracing, which is an impressive feat. And if I look in 4K, the final pass takes 6.2 milliseconds now. And then if I... Wait, why can I not disable always on top if the window is maximized? All right. So 6.2 milliseconds, and then if we disable blur, then it's like 3.8 or whatever. So this is a very, very significant cost, right? So obviously, but we are doing an insane amount of texture fetches here to have a white kernel. So clearly, completely stupid bilateral, but completely stupid non-bilateral filter is a bad idea. But to make it bilateral, all right. So I think what I have to do is I have to split it into horizontal and vertical passes to be less ridiculously expensive. And then the problem with this is that it will potentially introduce extra artifacts when we do bilateral filtering. But maybe it's not going to be too bad. So let's do bilateral filter first while we are here, just so that we understand what the results should look like, and then we'll see. Okay, so the way you do bilateral filter is you have to compare depths between the pixel that you're blurring and the pixels that you're blurring like into it, and then if the depth distance is too large, then you reduce the contribution of this pixel. And also I should mention, this is a box blur. What you should be doing is you should be doing like a Gaussian blur. It's been a while. I forget, it's like exp2. I guess it's probably, is it just x squared plus y squared? I forget what the Gaussian, so for now, let's just do the stupid thing. So to be able to fix this particular artifact, what we have to do is we have to sample the depth image. And then this is in a weird like space that it's difficult to reason about. Let's just invert it. This is a scaled version of the original depth. The more correct version would be like this, but I don't have the linear value here, so let's just ignore that particular problem. And then and again, you are supposed to do like some exponential weighting or something like this. So let's just do this. Let's just take the differences. And then I'll fix this later. So we'll take the delta between the depths. And then if it's 0, then the exponent of negative module of the delta is going to be 1. But then if this is a large value, then this is going to be a small negative value, and this is going to be closer to 0. And then we will incorporate this weight into our sort of calculation. And then this is making things better, but they are still terrible. So the actual linear value, you can also have like a factor on this. Oh, maybe you're supposed to square this as well. I don't recall. But the one particular problem is hold on. This is gonna be okay, yeah. Something like this. You can modulate the strength. So this is not quite the correct coefficient that you're supposed to use, but I'm not sure. There's not like a correct or incorrect way to do this. There is more correct and less correct, I suppose, way to do this. So with something like this, you can see that we don't have artifacts sort of on the border of objects, but we do still retain the blurring effect. So if you disable this, then this basically didn't change at all. but this has all of these artifacts that we would rather not see. And then with the bilateral filter, like, these are gone. So now the problem is all of this is way too slow. I was originally hoping that I could avoid doing the 2-pass filter because I was worried about the bilateral artifacts on the corners of the objects, but we don't really have a choice here because this is too expensive to not do in 2 passes. So let's do this in 2 passes. The way you do this in 2 passes is you run this shader twice. You have to first blur like horizontally and then blur it vertically. And then every time you blur in a different direction. So let's do that. And I guess while we are here, we should probably... No, that's fine. So let's specify the direction of the sort of filter, and it's gonna be like 1 for X and 0 for Y or something like this. So we will just say direction 1 minus direction times image size, and then we will do this. Wait, no, hold on. Offset scale or something like this. Okay. And all of this is a little bit wrong, but we will deal with this later. Oh, no, wait. I can't just multiply, of course. No, I can just multiply. This is fine. Yeah, and then instead of a 2-dimensional loop, we will have just a 1-dimensional loop where we go from like -8 to 8 or whatever, and then we'll just take man, hold on. Or I guess like this. Yeah. Okay, and then this is where we sample, this is where we sample. Okay, and then we will want to change this particular formula in the future, but for now this is fine. So if we just run this, then of course it will only blur in like one direction, whatever the direction is that we happen to use here. Or it might not even blur in any direction if this code is buggy, I'm not sure. So this should be 0, and so this should be 0, 1 over image size. I would think it's correct. Interesting. Am I? Oh, I'm not passing 0. I'm passing some garbage value that I'm not even sure what it is. Okay, so let's change C++ code to actually be able to do this. Now the naming is annoying now because this code blurs from the original shadow image that we've rendered into the new one that we've created. And if I want to do a second pass and I want to sort of blur it back, blur from the use the blurred image in one direction as the source and then save it back to the original image. And so now all of these names will stop making sense. But such is life. So we will refactor the names separately. So I will reuse the same shader. This is going to be shadow blur X, and then this is going to be shadow blur Y. So And then the second, so the first pass, oh no, yeah, this is 0. Interesting. Okay, so the second pass will use the same shader. The direction will be 1 instead of 0. I have a feeling this will not work for a reason I don't fully understand, but we will cross this bridge separately. And then we, the second pass is going to read from the shadow blur target and then write this back to the original one. This means the original texture now contains the fully blurred image. And then we'll have to do debug again to I'm not sure what I'm going to do if the bilateral artifacts are going to be severe, because you're not supposed to be able to split bilateral filters into 2 passes, but we really want to. How does this just work with no validation errors? This is concerning. Okay. All right, performance is like way better now. I should have some C++ code now, perhaps, that can toggle the blur on and off. But in 4K right now, we have 3.3 or something milliseconds for the final pass. And then if I stop doing this expensive blur stuff, then it's still 3.3. So that's good. The incremental cost of wider blurs is way smaller now. All right, so what about bilateral artifacts? Okay. All right. You're not supposed to do things the way we did them, but I guess it works. I will not argue with it works. And then let's say, again, we disable the blur, we enable the blur. So yeah, so the whole blur costs us 0.5 milliseconds, give or take right now, which is not ideal, but it's like the blur runs at 4K resolution. There's better ways to do this. We still have the interesting property of our shadows right now, which is that they can be pixel perfect. Sort of, or they can be close to pixel perfect, I guess. But because we are blurring them anyway, it kind of doesn't really make sense to do them at full resolution anymore. And so the thing we can do now, which probably makes sense, is to now like render or cast the shadows. Oh, this is horrible. This is box blur. I'm gonna fix this in a second. So we can now cast the shadows in, or like trace the shadows at a half resolution, and then blur the shadows at a half resolution. And that's gonna dramatically reduce like all our costs to the point where performance is pretty good. This is why I didn't want to spend a lot of time on obsessing over the extra cost of these compute dispatches, because like everything is going to change once we do half resolution shadows. So yeah, so these stair-stepping artifacts here are probably caused by the fact that we are doing a box blur, and what we actually want to be doing is we want to be doing a Gaussian blur. I don't remember. It's like probably minus I times I or something like this. Well, wait, hold on. What the heck is the... Oh, no, but there's a sigma. I don't know. And then if you are tweaking this value... Okay, there's still stair-stepping, so something is not quite correct. So I'm not doing something right here. Which is interesting. Oh. Oh, the stair stepping is because of the noise changes that I've made, perhaps? Interesting. Interesting. Okay. Uh-huh. All right. All right. Okay. All right. I mean, we still want a Gaussian blur, but I guess we are now doing a Gaussian blur. Okay. I will need to double check. These formulas are, I haven't done this in years and years and years. I'm sure the formulas are not quite correct. And yeah, the image quality sucks in certain cases. The good news is the wider blur is now more affordable. And the bad news is all of this needs to be tuned somehow. But maybe the correct thing to do is to first do half resolution shadows and then actually fix the issues. And I kind of want to switch to a different hash function because I stopped understanding the way we do noise right now is like super not how you should be doing noise. So that's a problem. All right, so let's separate these though. Yeah, these results are just not great at all. So there is this weird dependency between the between kind of what the noise is doing and what the blur is doing, but what the noise is doing right now is definitely terrible. So, and I'm sure this is not how you're supposed to use this gradient noise thing, but I don't even, I want to switch to a different noise function. Okay, let's commit some of this code, or maybe slightly clean it up and commit, because there's too many changes now, and there's like 2 new shaders, and I'm just gonna mess something up if I keep iterating on this. And also it's been 2 hours, 40 minutes, so actually we are close probably to the time that I have for this today. So, let's quickly refactor this code. We will have 2 passes, and then I'll submit this. We will have 2 passes, and in the first pass, the image, which is just a struct or something, yeah, but like we can do it like this. So, oh yeah, actually shadow source. So in the first pass, the source is the shadow target, and in the second pass, let's call this is the name target is now weird. Okay, let's call this blur from and blur to. So in the first pass, we read from the shadow target and blur into the shadow blur target, and then they are flipped. And then instead of using these names, we are gonna, so this is gonna read from wherever we need to read. Oh no, this is the destination, sorry. So this is blur to, and then this is blur from. This barrier was wrong actually. I'm not sure. Maybe I haven't rerun with the synchronization validation. So what you are supposed to do is do two transitions. So you're supposed to take the thing that you were blurring from, oh man, this is obnoxious. Hold on. A loop might be too aggressive of a refactor right now actually. I regret attempting to do this. Hold on. So my barriers must be wrong right now, because after I'm doing the first pass of the blur, what I'm doing is I'm taking the thing I have written to and transitioning it from write to read, but I'm not taking the thing I've read from and transitioning it from read to write. So what should actually happen right now is that if I compile and debug and then enable synchronization validation, then I should get like read after write hazard or something like this. Which I'm not getting. This is an emission, should be an emission in the validation layers, I think. Because this should not be correct. Because what should happen is we have a written to the one thing, but we have read from the other thing, and we are switching them around. Which is still, I guess, gonna work without validation errors. It's a little concerning that there was no validation error report, because I think it should have happened, but okay. So now that we have this structure, we can make a for loop. Because we need two barriers before and two barriers before and one barrier after. And so we are going to and then we can even transition. We can't transition from an, yeah, okay. Yeah, okay, so let's do the code. Let's write that code again, but now hopefully it's annoying that there's no error from the validation layers, because this means that I now don't know the code that I'm writing right now, is it correct or not? This is an omission in the sync validation, which is unfortunate. Okay, so first pass we are blurring from shadow target, and then second pass we are blurring from shadow blur. And then we need to take the thing we are blurring from, and then transition it from write to read. And then we have to take the thing we are blurring to, and then transition it in an interesting way. Blur to barrier. In the first pass, where we are writing to the image for the first time, we have to use a different barrier, and we had to do something like this somewhere else in the code. So this should not be like entirely new. Wait, that is a format. Okay. So these masks just change. In the first pass, the texture we are writing to hasn't really been used in this frame. It has been used in the previous frame, but that's a complicated thing we don't have to worry about. But in our second pass, we have just been reading from it, and now we are going to be writing to it. So this should be VK pipeline, basically the same thing, but with read instead of write. But this is also the same barrier that the validation layer doesn't catch. And so this is going to be impossible to validate because we don't know if this code is correct or not. Okay, whatever. In practice, this specific barrier is unlikely to cause rendering issues. So it's a more theoretical than practical concern. And then we still have to have one final barrier. And then this is the direction. Right, and then we have to actually switch the targets around. So this is the blur 2. And this is the blur from. All right, hopefully this one is correct. I don't know. All right, now it's complaining. Oh. Oops. Okay. We don't know if the barriers are correct, but we can't validate them in any better way. So this will have to do. So let me submit this code, and then maybe I'll do half res very, very quickly, and then we'll just call it today. So again, I don't know how much this stuff comes through on the video feed, but obviously we have not arrived at the perfectly noise-free shadows that are perfectly blurred and stuff. But that just tells you that all of this stuff is actually difficult to do. Since I haven't done things like this before, like I didn't really expect that I can do like in an hour that I can do perfect ray trace shadows, so that's fine. Let's just call it initial work on shadow noise blurring. We are now using a 2-pass bilateral filter. Well, we are using a sketchy noise function to jitter the rays we cast for shadows, and a 2-pass bilateral filter to blur the results. The results are a little nicer in some cases, but also noisy in others. So there's clearly room for improvement. Let's just call this that. Half resolution is non-trivial, by the way, because... Oh, and I probably want to bind a hotkey to disable blurring. So you'd think you can just do shadows in like half resolution, but there is a little bit of a question of in pixels like this, kind of, if you imagine the half resolution shadow buffer, which specific pixel do you cast a shadow from is not fully clear. So there's some stuff to fix. And yeah, like in areas like this where there is a significant divergence of the rays where they hit, whether they hit the shadow caster or not, there is a lot of artifacts when you move the camera. Did I change the noise thing back? Yeah, this is the original noise function as it was. And so for this, I'm not sure, maybe I can use a different noise function, but also maybe the filter should be wider. Like there's a lot of problems here. This one looks very nice. So this one I'm pretty happy about. And it costs us a little bit, but I don't think it costs us too much. So, and this area is also much nicer than it used to look like. So like in some, when the shadow caster is close enough, things work well. When the shadow caster is far, things do not work well. All right. Am I expecting this technique for shadows to have better performance and quality than something like cascade shadow maps? No. You can implement cascaded shadow maps, and the results are going to be faster. There's going to be some issues with biasing that we don't really have, but you can work around them. Then to actually get shadow like this, that, did I swap the contact thingy? Hold on. Well, the blur needs to be better, clearly. But to actually get shadows that have sort of proper contact behavior in rasterization, you need to do something like percentage closer sampling. So you can do all of this. I have implemented shadow maps too many times in my life. And I don't need more shadow maps in my life. But I don't think realistically you can get the same performance as shadow maps at the same quality level with ray tracing, but you can get better quality. Like, I'm not sure. But the more important thing to note is this. There's there's many other things that you can use ray tracing for, and many things that whoa, yeah, okay. There's more problems to solve. The noise stuff should be very different, probably. Yes, I'm happy with this, but now I get a lot more noise, I think, in the shadows than I used to get. Okay, so the thing we are struggling through right now, right, is how do we inject noise into ray tracing and then remove the noise from the output result to have the best of both worlds, which is to have an approximation of essentially cone tracing, but to get it from ray tracing to emulate things like shadow penumbras, etc., with decent quality and decent performance. But a lot of the stuff is extensible to other problems that you need to solve in ray tracing. Like if you want to do reflections with ray tracing, what you have to do is you have to get an initial noisy ray traced image and then denoise it using similar techniques and tricks and stuff like this. Some details are different, but some are similar. And so the reason why I want to do shadows with ray tracing is not because I think they should be faster and better with ray tracing, but because the idea here is, oh, how do you do everything complicated with ray tracing and then reuse as much of the technology between effects as possible. And I mentioned Cyberpunk. So Cyberpunk has a mode where they kind of do that. They don't do exclusively ray tracing. They have to rely on shadow maps for some backup stuff, and then I think they do screen space traces as well for some other stuff. So it's unlikely that you can ship a production game with 0 shadow maps and 0 screen space traces right now, but you can get closer to that. But yeah, no, of course you can do like cascaded shadow maps for this scene and get good results as well. And I'm also sure I have no experience with denoising, as probably is obvious from this image that's on screen right now, which is pretty horrible. I'm sure that somebody who has done all of these things before with ray tracing can get to a much better quality at the same performance that we have right now, like much quicker. Because some of the tricks you just have to kind of learn, and I don't really know them. I am curious though. Yeah, so the blur costs us around 1 millisecond right now, and it's like 11 by 11 or something like this. Oh, 21 by 21. Okay, that makes sense. There's better ways to do this blur. For example, one thing that we probably actually want to do is we are doing 2 texture fetches, and you can get away with just doing 1 texture fetch. The way you do this is when you do the initial shadow trace, you save a depth value or a depth related value to like the second channel of the texture that you're gonna blur, and then here you get access to both results for free for the most part. And so that probably would reduce the time that our blurring takes, which would be nice. But then there's also, so maybe I don't wanna, it's already 3 hours, I don't wanna have a 4-hour stream today. So I think maybe this is a good stopping point. Shadows are simultaneously better and worse than they used to be. Oh, this is actually horrible. This is probably, if I had to guess, a bilateral blur artifact or something like this. Oh, maybe not. Maybe this is just our usual noise problem. Interesting. 1 moment. If we disable blur. Oh, yay. Whoa. Oh, was it always like this? I didn't quite tune the bias properly. No. Is this? What is this? What the heck is this? Whoa. I'm confused. Oh, this is the correct shadow. This is how it's supposed to look like. It's just not obvious that this is correct, because this part casts like a shadow like this. Okay, and then we do noise, and then we have this really weird stair step. Okay. All right, so what the heck? Hold on. Oh, this is me multiplying things by 2, right? Yes, okay. All right. Okay, okay, all right. So the noise function, I will I didn't mean to commit that. Noise function clearly needs improvements. Actually, without this weird multiply by 2 thing, things are not as terrible as I was saying they were. So there's clearly an opportunity for improvement in all of this. But yeah, I don't really want to do half resolution shadows today. It's probably too much in one stream. So essentially the outcome of the stream today is we have made shadows even slower than they used to be because we've added blurring and you know, we have slightly increased the cost of ray tracing because the ray jitter makes it larger. But the benefit of what we've done today, in addition to sort of nicer looking shadows, is that we now have an opportunity to experiment more with denoising, etc. And we can now drop the shadow tracing resolution by 2. And in theory, we should be able to tune things such that they still look close to how they look right now. But that's going to be a substantial reduction in the total time. Plus, there's like blur optimizations that I've mentioned that are probably actually pretty easy to do that we could do. Yeah, okay. So I did not mean to commit the times 2. So that's kind of it. Obviously, the actual blurring and the noise will have to be tuned significantly. And it's not just tuning. Tuning implies fudging numbers, but there's some fundamentals that I'm pretty sure are wrong here. Like this is not. Why am I even squaring this? Isn't the Gaussian? You're only. This might be completely wrong. So the more consistent thing to do actually would have been to probably, there's like a correct formula for this. I could Google this in 5 seconds. I don't want to do this because because the stream is basically at the end. But was there really a square in the Gaussian kernel formula? Hello. Am I applying this value? I am applying this value. It's interesting that this is definitely wrong for many reasons. All right. Oh, maybe, yeah. Okay. All right. Let's just keep it like this. I will need to actually look at the correct Gaussian filter weights later. But maybe this is not too bad. Okay, so I think this is kind of where we'll end this. Future work performance can be increased both by tactically tweaking the blur filter, by like reducing texture samples by 2 at least. The other thing you can do here is you can use the gather instruction maybe to, yeah, you should be able to use gather to get like 2 pixels for the price of 1. Then you might as well blur 2 pixels. So there's like a lot of possibilities for improving the performance of this. And then you can just drop the resolution by 2 by 2 for the shadows, which I want to do as well, because that will get us back to the kind of, oh, everything is very fast. Now we can add way more stuff to look nicer. Right now, if you look at the overall performance at 4K, our entire frame is like 6 milliseconds. So 6 is, you know, you can still render at 144 hertz, but you're at the limit of 144 hertz basically. It's like 7 milliseconds, not 6, but you're basically there. And so if you wanted high refresh rate rendering for this renderer at 4K, then you can't increase the shading complexity. You have to substantially increase performance first, and then actually be able to afford more effects. But okay, after unfixing the weird noise stuff that I've done, actually the results are good. I'm actually fairly happy with the quality. Performance needs work. Performance needs work. All right, let's see. Yeah, it's parameterized via this hack. I mean, usually you just pass a 2D value. You can pass a 2D value here, like whatever. Because you just need x, y, and y, x, I just pass a scalar to parameterize the direction. And yeah, like in theory, bilateral filters cannot work when they're separable. It's just in some cases the artifacts that you get from the separation are visible, in some cases they aren't. Gaussian filters without bilateral are separable. The mathematical equivalent, like you can do x plus y, or you can do x times y and it's the same. But bilateral should break it, but in our case it doesn't, which is nice. Shouldn't the noise offset be added in light space instead of world space? Yes, this is the thing I was talking about when I was saying this actually should be a cone, not whatever the heck we do here. Whatever the heck we do here is we are just saying, oh, so you should be adding this. You should be shifting in 2 axes kind of orthogonal to the light direction. But if you shift an xz, then unless the light is like very at a very steep angle, it's close enough. But yeah, like this is incorrect. This is a hack. So maybe the other to-do that I'll add here is this should actually be doing cone sampling, not random xz offsets. And cone sampling is different from xz offsets because the cone may be oriented different. So yeah, the noise should be added in light space, not like xz. It's just, again, I need to look up math for this and I don't want to do this. But that is the astute observation and correct. All right, I think we are done for today. Thank you people who have joined this completely random impromptu stream. I don't know when the next stream will happen. We'll see. I mean, maybe next weekend, maybe not, we will see. But the follow-up work is basically performance. And then if we double performance or more, ideally we like triple performance of shadows or something like this. Because if you look at the cost of the final, of all of the passes that run like at the end of the frame in 4K, it's like 4.7 milliseconds. And then the cost of everything that happens before this is a little bit over 1 millisecond. So if this thing was 3 times smaller, this would put it at around 1.5. And so the total frame would be around 2.5. And so that's the point where you can be like, all right, cool, we can now spend more time to get nicer graphics. This image is not too bad, honestly. It's just that in motion, I think the biggest quality problems that we now have, after I fixed this noise stupidity, actually, even in motion, it's bad from far away. And it's bad from close up in these penumbra regions. But it's not completely terrible, I should say. This is the problem with screen space filters, by the way. So like what happens, so like at this distance, these shadows look completely fine. At this distance, you can see the obvious stair stepping. And the reason why this happens is we are doing the noise in screen space, sure. But the way the noise affects the final output depends on the distance from this point to the caster, which is very large. And so what happens here is that you kind of have to have the blur width scale. It can't be constant in screen space, because the jitter that you have, the effective jitter of shadows that you have, or okay, let me rephrase this. You want to have the filter width be the same as your penumbra size. So that if the shadow is blurred over a large fraction of the screen, this is what your filter should be blurring at. And so here, our entire screen literally is the penumbra. And so the only way to correctly render this would be to filter over the entirety of the screen. I think the production, I could be wrong on this. My impression was that the production denoisers for shadows, they like build a mid pyramid so that they can filter at half of the screen without actually, incurring the cost of filtering across half of the screen, by having this progressive, like, pre-filtered result that then they can sample from, or something like this. I haven't looked like super closely into this. But until you get like right into the shadow penumbra that's very wide, actually things look pretty nice. So I'm actually pretty happy with this. I'm still skeptical that the noise that we are doing is like the correct type of noise, but things are actually pretty nice. Just don't get too close. And things will be fun. Okay, so I think this is it for today. Thank you people for joining. Whenever the next stream is gonna happen, hopefully this time I will actually pre-announce it before the weekend starts. And that is it.